Hi everyone. Today I'm going to talk about this paper called Direct Preference Optimization. Your language model is secretly a reward model. And this is a work by Stanford team. And this paper was one of the recipient of the Best Paper Award at NeurIPS 2023. And yeah, so let's go over this paper. So some background. So as you know, uh, pre-trained large language models on bulk test does not naturally give a language model that responds to the user intent. So just purely using a pre-trained language model doesn't gives us interesting like responses that aligns with humans. For example, in this example, as you can see, the prompt is explain the moon landing to a 6-year-old in a few sentences. And using GPT-3, it just decides some random patterns. For example, it just responds as explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old in a few sentences, and blah, blah, blah. What we would like to get is a model that understand questions and instructions, something similar to ChatGPT like models. So the standard way to train and fine-tune uh, a language model and create something like similar to ChatGPT is uh, consists of like 3 steps. By the way, this is from the Instruct GPT paper. So if you are interested to learn more about this is the paper by OpenAI, training language models to follow instruction with human feedback. But I quickly go over the high level of this paper. So basically it has 3 steps. Step 1 is to collect demands. So first of all, we start with some pre-trained language model, and the first step we do supervise fine-tuning. So basically we a prompt is sampled from our prompt data set, and we have labeler that demonstrate the desired output behavior, and we just simply do next word prediction on this new data set, and we call this step supervised fine-tuning. And this step sort of know how to answer to question and instruction. So by itself, if you just do this on a pre-trained language model, we should be able to get some sort of aligned language model similar to ChatGPT. However, this is not enough. And then the next step to do is to construct a reward model. So basically, we start from this policy, which we call pi of supervised fine-tuning. We sample few prompts A, B, C, D, and we ask human labelers to rank them from best preferred to less preferred. And then we construct a reward model. And I'll go over the optimization of the reward model later. But here I just want to quickly describe the whole process. And the last step is to, once we have this reward model, then we use a reinforcement learning procedure to further fine-tune the policy. And this step in the literature is called alignment. So basically we have our policy, and it just sample a response, and then we have a reward model that can assign a score to the response from the policy, which we get the reward, and then we use some sort of actor critic algorithms such as PPO. So it doesn't have to be PPO, but PPO is the first algorithm that was used by OpenAI, but other RL algorithm can also be used. So that's basically the whole process of how we fine-tune the language model. And so sort of going back on the second step, which if you recall, I described the reward model. So I'm going to explain in details how we train this reward model in more details. So basically we sample a few responses from the supervised fine-tune policy, and we ask labelers to rank them from preferred to less preferred. So in this example, imagine we sample two responses. One is called YW, the other is YL. YW is preferred over YL. So we have these kinds of data set. So we have a prompt, and then we have two responses, YW and YL. And then what we do to train the reward model, we basically use this loss function. So this is the so-called Bradley theory, which connects the rewards to preferences. So it's a sigmoid function over the score of the preferred response and prompt minus the score of the less preferred response and prompt. So that's the Bradley theory model. And then we can use just negative likelihood to just train this reward model. So pretty straightforward. This step is pretty straightforward. And then once we have this reward model, what we want is to optimize for this objective. So which is we want to maximize the reward. So we sample from our policy, which is we start from the supervised fine-tune model. Sorry. And then at the same time we want to keep KL, divergence to original model, small. We don't want to diverge too much from the reference model. So what we want is to optimize this equation. And for this, so this is the third step of fine-tuning, which we call alignment. And usually we use, like I said, we can use any actor critic RL, but this step is not easy and it's pretty complex. So recently there was another paper which is Secrets of RLHF in Large Language Model, Part 1, PPO. And I'm not gonna go through the whole process of PPO, but you can see that it's just pretty complex to just do the alignment using the RL and PPO. So the PPO workflow is gonna be too complex, and just looking at this diagram, it's very complex. I'm not gonna go through this, but the motivation to show this is it's just complex to do this step. So then that's the motivation for this paper. Can we bypass this step of RL fine-tuning, which is pretty complex, which enables the extraction of the optimal policy in a closed form without any RL training loop. So that's the motivation. So we start from this objective, and if we just start from this objective has a closed form solution. Actually, this is not the contribution of this paper. So in previous work and previous studies by Sergey Levin, we could show that the closed form solution of the optimization problem in equation 3 can be expressed as this equation. So basically it's a function of the reference policy with some weights on the reward. So that's a closed form solution, and where the z term is the sum over all the possible responses with some function of the reward. So that's the problem here, that this term is not interactable, because basically we have to sum over all the possible answers, all possible y's. So basically this is not interactable. Then what this paper does is, okay, starting with this closed form solution, with some algebra we can get the reward in terms of the policy. So basically you can just simply take the log of the each side of this equation and do some algebra, and then we can get the reward. Do some rearranging, so then we can get the reward in terms of the log of pi of r versus pi of reference for the response, plus some function of the prompt. So this ratio is positive if policy likes response more than the reference policy, and it's negative if policy likes the response less than the reference model. So still we haven't got rid of the z term, but at least it's some function over the prompt, not the generated responses. But if we substitute this reparameterization in equation 5 into equation 1, so basically we have the reward in terms of the policies, and if we just substitute it in our loss function in the Bradley-Terry loss, which is sigmoid of r of the good answer minus r of the bad answer, and our r is based on the policies, then fortunately the z terms cancels out, and what we end up is equation 7. And the nice thing is, again, our reward is based on the policies and the z terms cancel out, and we can just simply use this loss function to train our policy, and then we can bypass the RL fine-tuning step. So that's the whole idea of this paper. It's pretty straightforward. it's one of those papers that you kick yourself, why didn't I came up with this idea. It's simple and it makes a lot of sense, and again, once you look at it, it seems simple, but nobody has thought about this until this paper came out. So that's the whole idea of the paper. I'm not gonna go through the results. Feel free to go over the results. Next, what I'm going to do is just go over the implementation at a high level. I'm not gonna go through every details of the implementation, but what I'm hoping is to give you an idea of how to implement this paper, and then if you're interested, you can just go over the details yourself. So here is the original implementation by the author, Eric Mitchell. And yeah, so going over this implementation at a high level. So basically we have a bunch of config files, and then we have a train function, which is our main function, and our trainers, and some util function, and some function to create the data set. So our config is basically specifies some hyperparameters, the type of the loss, and you can go over the details, but so we start with this config file, and this is our main function. Again, my hope is to give you an idea of how to implement this paper. So I'm not gonna go through every details. So yeah, we have our main config file, and basically starting from here, so we have a policy. I'm not gonna go through the supervised fine-tuning step. I am just gonna go through the deep the fine-tuning step. So assuming but this implementation has the SFT step, but assuming we have done the supervised fine-tuning, and now we want to do the alignment, which is the DPO loss. So here is how we can do it. So we can start from some policy. So we can use any model. So we can use some Hugging Face as existing model. So in this case, we can use this model, and we basically disable the dropout. And for DPO, we need a reference model. Reference model is gonna be the same. Again, assuming this is the supervised fine-tune model, and we initialize a reference model as well. I'm not gonna go through the parallelization and setting up the GPUs and those things. Here I'm just gonna go over like the main part of the implementation. So once we initialize the policy and reference model, let's go through some other steps of the implementation. So then we initialize a trainer. So there is so basically train and trainer are two main like important parts of the implementation. So we initialize our trainer. So if we go to our trainer, so let's go over the basic trainer. So in the basic trainer, the way we initialize it, we need a tokenizer. We initialize our tokenizer, and then we have a policy, we have a reference model. Another important function is the batch iterator, which let's go over to this function. This is also important. So basically this is an iterator, so we can just, so it has different parameters: tokenizer, batch size, shuffle, max length, number of epochs, blah blah blah. And again, I'm just gonna go over the important part of the implementation. So this function, just yeah, this is just iterator. So basically it yields a batch, but for that first we need the data set. So what this paper uses for the dataset is the anthropic helpfulness harmlessness dataset, and this is how it creates the data. So again, let's go over through this. So basically this is the HH dataset. Like I said, it is helpfulness harmlessness dataset. So we get the data. So let's see how this function is implemented. So basically the dataset is converted to a dictionary with the following structure. So we have a prompt and then a dictionary with responses, which is a list of a string, pairs, which is a list of tuple of int, and SFT target, and second prompt, and blah blah blah. Just to give you an idea of how this dataset looks like. So let's see if I have this. Yes. So here is how the dataset looks like. So each data has a chosen and then I believe a rejected response. So basically this would be our prompt, and for chosen this would be the response, and for rejected it's the same prompt until this and an assistant, and then this would be our response, which is not preferred. And this is what this function does. So again, the prompt should be structured as this, like I told you. And so we load the data set from the Hugging Face, and we basically create this dictionary that has pairs, responses, and SFT target. And this would be our data. Okay, so this is how we load our data, and we format it into this structure. So let's go back to, okay, so this would be our data set. And once we have that data set which has these keys, so it has, so we have a prompt, and then the data has different keys, responses, pairs, and SFT target. So basically we create this flat data list, and that would be our flat data. And then we have a collate function. I'll go over it in a second, but let's see how we use this. So we can shuffle this flat data, and again, I'm not gonna explain the SFD part, but I'm just gonna explain the DPO part. So for the DPO part, the next step, once we iterate over our flat data, which is consists of prompt, responses, pairs, SFD, and truncation mode. So basically, we first tokenize prompt, responses, the chosen response, the rejected response. So let's quickly go over this part. Tokenize batch element. So again, for DPO, this function, we have a prompt, we have a chosen response, and we have a rejected response. So we can just use our tokenizer to tokenize the chosen token, and then rejected, and then the prompt, and we append the end of a sentence token ID, and for attention mask we append 1 because we want our model to pay attention to this token. Similarly, for rejected token, here we do some truncation. I'm not gonna go through this. You can simply go over it, and so basically just do some truncation from the prompt, making sure it's less than our max length. And then what we do is so basically we want to fit the prompt plus the response to the model. So as you can see here, we have chosen sequence token, and it is the prompt token plus the chosen tokens. So that would be the chosen sequence token. And similarly, for rejected sequence token, we want to fit prompt plus rejected. And our reward basically is the chosen sequence token input IDs. However, we don't want to generate loss over the prompt tokens. So basically we mask the prompt tokens. So we use -100 for prompt token. Similarly, for rejected one, that would be our label would be rejected sequence token, which is prompt plus rejected tokens. We just copy it as label for rejected sequence tokens. Again, for our loss, we want to mask it. We want to mask the prompt portion of the sequence. So that's what this section is. And then we create a batch. So we have our prompt, we have the chosen, which is the prompt plus chosen, the rejected, prompt plus rejected. These are the actual like text. And then chosen response only is just the chosen response, rejected response only is just the rejected response. And we then create the chosen input IDs and other part of the batch here. So yeah, and then chosen labels, and then we just create this batch. So that would be our batch. So, and this just tokenize a single batch. So let's see, let's go back. So that would be our batch element. And okay, we need this part. So that would be a batch element. We just append to our batch, and once it is equal to batch size, we do yield on the collate function. So let's quickly go over the collate function. So usually, as you probably know, we use collate function to make sure each training example has equal length. So this is the way we initialize it. So let me go quickly over it. Again, the goal here is making sure we have equal length for all the training example. So this is how we define our collect function. We basically first and single detail here is for prompt. We want to pad the prompt from the left. So typically we pad on the right, but for prompt we pad it on the left. So here is just to reverse the tokens if it is a prompt token, and for others it's just the tokens. And yeah, we get the padding value, and if it is labels, the padding value is -100, and we use this PyTorch function to do the padding. And since for prompt we reverse the order of the tokens, we just flip the second dimension, which is the sequence length. And yeah, so that's how the collect function works. It's basically making sure we have equal lengths for our examples. And then that would be our collect function. So let's go back to where we were. Yeah, so then we yield a batch, and we keep doing this until we iterate over our training examples. So that would be our get batch iterator. So now going back to the trainer, so that would be our train iterator. So we do the same thing for the eval iterator. I'm not gonna repeat the same thing. So that would be the way we initialize our trainer. And then it has also a train function. Let's see. Yeah, so we have a train function that we can go over each batch in the train iterator. So it has an eval function based on eval every. So we do eval. So I skip that. I go over the training part. So here we initialize a batch metric that we add our losses and other metrics here. So this is the important function here that calculate the loss and other metrics. So basically when we do train, we call this function. So let's go over this function quickly. Yeah, so we get a batch and some other parameters, and then it returns losses with some metric. So let's quickly go over this. So again, I'm going to explain the DPO part. So what for DPO we want the policy chosen like probabilities and policy rejected like probabilities, and we want this for the preferred answers and less preferred answers. So what we do first is we do a concatenate forward. So what this does is run the given model on the given batch of input, concatenated the chosen and rejected. So basically we just concatenate the input for our batches. We concatenate chosen and rejected, So if we quickly go over the concatenated input, let's go over that. Basically it's just we do a torch cat, that's it. So what we do here is yeah, first we get the chosen response, and we pad it to some max length, and what we do is we just do a torch cat on dimension 0, and we just get the concatenated batch. That's as simple as that. Let's go back to where we call this. So that's our concatenated batch, and then we run it through our model. So basically we feed the input IDs and attention mask, and we get logits. We get all the logits. And then what we want is the log probabilities to calculate the loss function. Then the next step is to call this function, get the batch log probabilities. So basically we have our logit, which is of the shape, batch size, sequence length, and vocab size, and our labels, which is batch size, sequence length, and minus hundreds are ignored. Those are our masked token IDs. So what we do is, so we have our logit, we can get its log softmax, and then we have our labels. We do a torch gather to get the per token log probabilities for the label IDs. That would be our per token log probabilities. It's pretty straightforward. So again, we just want the log softmax probabilities for our label IDs. So again, we have our logit in this shape, batch size, sequence length, vocab size, and then this is batch size, sequence length, and what we want is to only to get the log probabilities for only our label only for our label IDs. So that's what this torch gather does. And yeah, and we don't want to calculate the loss over the mask labels, and this is this loss mask, and let's ignore this part whether it's average or sum. We just let's just get the sum, which gonna be of the shape batch size. So that would be our batch log probabilities, and this is our all of the log probabilities, including the chosen and rejected. And given the way we concatenated them, we can just get log probabilities for chosen and rejected, and this would be our concatenated forward. Yeah, so we get the chosen log probabilities and rejected log probabilities. We do the same thing for reference model, and making sure we do torch no grad, because we don't want to train the reference model. And for DPO, let's see, and this is the way we calculate the preference loss. So basically we have our policy chosen log probabilities, policy rejected, reference chosen, reference rejected. So basically all these terms that we need for calculating the loss. So we have 1, 2, 3, 4, and we also need beta. So these are all the all the inputs that are needed. And yeah, just quickly going over this. So basically this part is policy chosen like probabilities, policy rejected like probabilities, and reference like probabilities, reference chosen like probabilities, and reference rejected. So what we are going to do is it's just calculating this loss. So we have this logits, which is this part without beta, and here does so ignoring the smoothing part. Here does add one additional step, which is just smoothing, but imagining this is 0, it's just this loss function here. So basically it's just beta multiplied by logits, which is pi like ratios minus reference like ratios, which is this part. We just multiply by beta, and then we do log sigmoid. And yeah, just here it does another thing, which is smoothing. So basically we multiply this with 1 minus label smoothing. If the labels are noisy, then we do this step, and you can go into the paper, the appendix of the paper for more details. And then we calculate the chosen rewards and rejected rewards, and that's pretty much it. This is gonna be our losses, and yeah, I'm not gonna go over other things. This was basically the main important part of the paper, and yeah, you can go over other implementation detail, but I just wanted to give you an idea of the way this is implemented, and I hope this was useful for you. And yeah, thank you so much for listening, and if you stick around till the end, thank you for paying attention.